Hey guys, this is my presentation on using BPF for filtering in Golang. I'm assuming most of you haven't seen this movie, but that's okay. There are at least a couple of people who have, and that makes me happy. This is obviously not the name of the movie. Start with the who am I? I'm David Girard, third year cybersecurity. You should go see the world, go adventure, go on vacations. You have your whole life to work. You might as well go see stuff while you can. Got a lot of great photos up here. My dog, my other dog, my girlfriend Emma, a couple of my friends, Maxim and me when we worked at FM together. Girard in the bottom left there. He's a cool guy. I miss him. So let's start. Oops, that was two slides at once. Let's start with some background. So BPF stands for Berkeley Packet Filter. If you've worked with Kubernetes, you've probably heard of eBPF, which is Extended Berkeley Packet Filter. That's like the cool big kid version for when you're actually good at what you do. I used like the simple version. But in essence, BPF is a kernel feature for fast packet filtering in Linux. It's built into most Linux kernels now. It first came out for just network packet filtering. That's the legacy BPF, and that's what I used. And then extended Berkeley packet filter is the more modern version where you can actually get very feature-rich things. And I'll go into some of the limitations of traditional BPF later, and it'll make more sense why there's an extended version. So for legacy BPF, it exposes part of the Linux kernel's networking stack to user space and lets you run sandbox VMs for processing packets directly from the data link layer. And this is like ridiculous because you can get really, really fast packet, not only filtering, but just like handling. And you can build some really cool programs out of it. And the reason that I chose to look into it is if you use BPF filtering in combination with raw sockets, you can bypass host level firewall rules. So that's things like NF tables, IP tables, anything where you'd write like drop all. And when you use these together, you can get through and make like a cool red team tool. Or you could do something useful like logging metrics, stuff like that. But I use it for red team. And I'm going to show it mostly by talking about it and then walking through sort of the process of how do you make a filter, how do you look at network bytes, how do you actually make something meaningful out of packets coming across the wire. There's more background information on BPF. It's a very small virtual machine. That's where the speed comes from. And the fact that it's built into the kernel is where you get all your advantages. Some real stuff you can use it for is you can measure packet transmission times without impacting the actual like processing speed of that application. So if you have it built into the payloads of each, every transaction, you can use a BPF filter to read that and pull data from it without having to process it inside of your application. And then also you don't have to rely on anything above layer 2 if you don't want to. That's a really cool functionality. That's where the red teaming stuff kind of comes in. And then yeah, it just has a smaller footprint also. If you want to use eBPF and Go, you have to write a bunch of code in C, which then you have to like build into your tool chain, and it's kind of messy. It's really not messy, but I have like a small brain, so it's kind of hard for me. Raw sockets are another really important thing that's going to be a part of this. I'm not going to go too deep into them because they're very complicated, but you can choose which layer of a packet you're examining by using correct raw sockets. And you can use BPF in combination with that, like I said. And there's a ton of options, and I have some of them listed a little bit later on. But the goal for this presentation is to sort of understand how to use BPF for filtering by first looking at, how do we filter packets? Once we know how to filter packets, how do we go through edge cases? Once we know how to go through edge cases, how can we actually do something cool? So for me, that meant processing packets regardless of whether the packet was TCP or UDP, and regardless of which layer 7 protocol, in other words, like which port it came across. How do we put that into an application? And then how do we set the groundwork for making our own protocol at layer 7 to do some pretty swifty things? So sockets. Like I said, there is a lot of information and a lot of options. Like a ridiculous amount of information and a ridiculous amount of options. There's a really cool animation, but this is like 5 hertz, so you don't get to see it. But in about a second, we're going to see a really funny image of a sunflower. But yeah, all of the images that are coming up, it's just like piles and piles of documentation, and it doesn't conflict, but it is really hard to work through and see what matters. And so I was really struggling with that for like a while. And then there's this guy. This was like crazy. I was on Stack Overflow. This guy, Mo_, he just goes, I created a graphic to grasp the concept more quickly. This answer had like 7 upvotes, and he dropped like every option that would be necessary to understand the raw sockets, which was crazy. And then this guy has like no other posts as well. It was a total drive-by. But when we look at this, we can see what we're really looking for, which is we can get all the way down to the layer 2 header, and we can get it as something that we process. So essentially, we can get all the way down to looking at like just above the preamble of each packet. So that's the MAC source address, MAC destination address, and what, IPv4 it's running. And so the reason that this is important is because when we want to make an actual raw socket, we have to know what we want to put on the file descriptor. So in Linux, whenever you're making a connection, whether it's for inter-process communication or between machines, you need sockets to communicate. And specifically with Golang, it uses the Linux syscalls and the Linux headers. And so when we want a raw socket, we have to know AF packet, which is what gives us the raw socket, or sorry, sock raw, which gives us the raw socket, AF packet, which if I go back a slide, in this diagram, AF packet is down here. This is what lets us access the layer 2 headers, which is really important, again, which we'll see very soon. And when you kind of put all of that together, you can get the raw sockets, you can get what part of the datagram that you'll actually be reading off the wire, and then all that's left after that is the eth all, which is just saying, like, give me everything that's coming across the Ethernet protocol. And then the rest of that's just like boilerplate for opening up the sockets. And then there's at the bottom, there's create send socket. That'll come back later. I'll explain it a little bit more. So the first thing I had to do was look at the actual Ethernet frame and see like where the bytes would be when I was trying to filter the packet. You can see at the front there's the preamble, but we read just above the preamble because we don't really need it. Specifically, we can see for the first 6 bytes, we have destination address, then source address, then we have the type, and then the remaining is all for data. And so the first thing we want to filter by is making sure that we're not trying to read any packets in our program that aren't IPv4. And so our very first filter is just going to be using the raw BPF. Load absolute, it's basically an assembly program. And so you want to load in the absolute offset of 12 bytes, which will give us the start of where the type of packet is. And then the size is 2, which is 2 bytes, which pulls these 2 bytes. This is straight out of Wireshark. And we have just a jump instruction for if it's equal to what we want, IPv4. And if it is equal, it'll skip over the next instruction and go to ret A. Ret constant, it returns a constant value from the BPF virtual machine, which you can use for all kinds of information. And in this filter, we either return 0, so for that would be like dropping the packet. Otherwise, we return what's in register A, which is just the packet itself. So the next step after that is looking at the IP layer. I didn't do a lot with the MAC addresses because the only filter we really needed was like, did I send this packet? No, let's process it. So at the IP layer, we have this command called load memshift in BPF. What this does is if you've ever looked at like in Wireshark, we have version 4, which is just IPv4, and then we have the header length, and it's actually in the byte. The first 4 bits correlates to the version, and the trailing 4 bits correlate to the header length. Load memshift allows you to load in the 1 byte from the IP layer, and it'll just calculate the header length in bytes from there. And that's really helpful because the end goal of this filtering is we want to find the start of the data section in TCP or UDP and know for certain that the right byte we return is where that data starts. And in IPv4, there's a professor that would disagree with this, but you can actually go over a header length of 20 bytes and have it still be a valid packet, and I wanted to account for that edge case. And so in order to do that, we needed load memshift to shift the memory and load it into register A to have the header length. Before I go to the next slide, there's register X, register A. You basically, in BPF, one of the main limitations is you only get 2 registers for storing data that you use in operations. So you have register A, which is just your first register, and then register X, which is where you can load additional things for operations. So for example, when we do multiplying, you might have like 4 in register A, and if you wanted to multiply by 5, you'd put 5 into register X. And there's a couple of ways around that, but that's one of the primary limitations that would be like, if you're doing something serious, go to eBPF. So it's kind of a word vomit up to this point, but this is where you're actually doing filtering. So there's a lot of commands that are going to be very similar. We have the load memshift we just talked about. We have jump if, load absolute. All of these things, they just correlate directly to assembly instructions, and actually exposed in Go, when you have these values, you can actually pull out the like bytes that make up the assembly code if you wanted to. But the first thing we're going to do is we want to check for TCP and UDP when we're trying to make it agnostic for both of them, because they have different locations for their data. There's more information in the header for TCP, and it's also not fixed, whereas UDP has less information and it is fixed. So the first thing we do is we load in the offset for where the IP protocol is stored. The IP protocol is fixed where it's stored in the frame, just because of how IPv4, the IP layer, is written. And so that starts at byte 23, and it's 1 byte long, and we have 2 different fixed values. For TCP, it's aux06 and then aux11 for UDP. And all we're doing is we're loading in the value at that offset and then comparing it against either TCP or UDP. And if it's neither of them, it won't jump over that return constant, and it'll return 0, which will drop the packet. And the next thing after that is that we have the load memshift we talked about. This is where we're going to get the header length of the IP layer. And then all that's going to do once it gets it is it's going to move the value from register X to A. So memshift puts that header length into X. We move it from X to A. And then we can add a constant. We want to add the constant value for the length of the Ethernet header, which is from the Ethernet layer, which was the source MAC address, destination MAC address. And then finally, when we add those 2 things together, we get the start of the layer 4 protocol that we want to read from, which is either TCP or UDP. A lot of words explaining this, but there's a payoff, don't worry. And then finally, we can write that back into X so that we can use a command called load indirect. What load indirect lets you do is you can take a value in register X, and you can load an offset relative to the value in register X. So take a break for a second. Now that we're on to layer 4, we've found where the layer 4 packet starts, and we know that we can start reading with load indirect. There's 2 things we need to do. We need to find the data section in TCP, the data section in UDP. TCP, there's some nonsense we have to think about with the 3-way handshake for later on when we send packets. And then we also have to think about what makes it a protocol, what are the expected behaviors, and things we have to look out for when we're trying to parse the packets. So the easier of the 2 is the UDP datagram. This is straight off of Wikipedia. This is fixed, right? So it's 2 32-bit words, in other words, 8 bytes of data. And in that 8 bytes of data, you have your source port, destination port, length, checksum, and then your data starts. So it's very easy to write a filter for UDP because you just have to jump over 8 bytes. So you may remember when we moved from register A to X to use load indirect, we're now going to use that command. We're going to load a constant value into register A, which is the fixed header length 8 bytes. And then we can use alu op X. That is how you take the value in register X and use it like the multiplication example I said earlier. And then finally, what that will leave us with is in register A, we'll have the start of the UDP data section, which is this big block here, because we'll have taken from bit 0, the start of layer 4, and added the header length to get all the way to data. Unfortunately, TCP is not as easy. So for TCP, we have 2 problems. 1, TCP has options that can extend the length of it before data starts. And 2, when you send TCP data, if you tried to do it by just sending like a TCP packet, before it actually sends your data, it'll try and do the 3-way handshake. And the problem with that is that we're expecting the port we're sending this data to be dropping all packets. And so that SYN packet will get dropped, and your data will never actually get sent. So what that means is we have to find a way later on to make sure that the initial SYN packet has that data inside of it, which is not the expected functionality unless you're doing a fast open. And here's a state diagram where it says like you'll receive a reset if the port's closed, and that's really just reiterating what I went over. But getting into the actual datagram, what we have is we have source port, all the things you expect, all the things you want, and then our problem, which is options if present. So if options are present, then we can see that we'll be starting at a different byte than we otherwise would expect to be. And that's kind of a problem because there usually isn't options, which is convenient, but also means that we just have to make sure that we're calculating our next sort of byte that we're reading based on the data, sorry, not the data offset, based on the size of the header. And I have some way that I did this that's escaping me because I'm trying to present this. So this is the filter of doom for BPF with TCP. Oh, the data offset. Oh my gosh, it tells you where the data starts. So we read where the data starts with a load indirect, and where the data starts when we actually look at the packet, you can see that these headers up top are fixed in their position. And if you go down 0, 4, 8, 12, we get down to where data offset starts. So data offset is the first 4 bits of the first byte. And so we need to load starting at that byte. And we have to use 2 shifts. So we shift to the right by 4. That will drop the data that's reserved usually, so empty. But we need to get our actual number of how many 32-bit words are in the datagram so that we can use it in multiplication. So what that basically does is if we look at this, we can see that data offset is in the first 4 bits, and then the last 4 bits are reserved. We move data offset to where reserved is. That way it actually reads as the number it is instead of much higher. And there's a couple of ways you could have done that. I chose to do it by shifting the bits. And then you just have to multiply by 4 because it's in the number of bytes. When you break down the math, it's like the number of 32-bit words. It just simplifies down to multiplying it by 4. But you can see I use load scratch. You have a couple of things where you can store information. You just can't use them in operations, and that's what scratch is. So you can't access it with ALUOP because it's not a register, but you can load to and from scratch. If you need data later on, you just don't need it at the moment. So what this filter is doing is it's getting the length of the data offset, and it's doing some math, and then finally we're getting it into our register the same way that we did with UDP so that we can use load indirect again on top of that filter in order to access the actual start of the data. And the good news is that's pretty much the end of the difficult filtering. So all we have at this point is we're reading the data of either a TCP or a UDP packet. It could be either one at this point, but it doesn't matter because we know that we're reading from the start of the data. And for me, I put the first 8 bytes as shadow because that was the name of the tool. Those are the magic bytes that identify a packet as being one that I want to pick up on. And all it does is it reads those bytes with load indirects, returns 0 if there's nothing that we want. And then the magical part is that if it was what we wanted, it stores the end of the magic bytes into register A and then returns that. And what that means is that when we go and we run this virtual machine on each packet, we'll either get 0 for a dropped packet, or we'll get a number for the byte slice of where the data we want to read for a command or otherwise actually starts. So to actually create a virtual machine, everything that we just looked at was a bunch of BPF instructions, and those are put into a BPF instruction slice. And then all you have to do is pass that slice into bpf.newvm, and then you get a virtual machine with your BPF program that's ready to process as many packets as you want at a very, very fast rate. And so that's what this function does. And an interesting thing you can do is you can actually write test cases really, really easily. Because it's using the bytes directly from the packet, you can basically just capture them from Wireshark and then copy and paste them into a byte slice and then run those bytes through the virtual machine as if it was a packet you just received. Which is really cool because when I was testing TCP, it was really hard to tell if I was getting the right offsets, and writing test cases helped. Who would have thought? So the other thing that you should consider doing is creating a struct for your data. Because this isn't using the net HTTP package, users will just be getting a slice of bytes returned to them, and that's kind of meaningless, and it's not very kind to force them to parse it themselves. And so I made something called Shadow Packet because the tool is called Shadow, where you can get the source address, source MAC, destination IP, destination MAC, and all those sorts of things, and it's just got some boilerplate code to return it. And all of that is because then we can expose, also you have to make the sockets. Remember the slide from earlier? The create send socket, I won't go into it too much because it was a whole other mess. That's how we send the data in the initial TCP packet to imitate a fast open, but that's messy business that doesn't really need to be covered. But once you have the create a VM and you have the receive socket made, we can make a channel of our shadow packets, and then we can write a function to basically listen to the raw socket, get every slice of bytes that comes through it, run it through our virtual machine, and then if it's a number that's anything other than 0, it'll load the data from that payload into a shadow packet and return that to a channel. And so that's what we expose from my module for this, so that all the end user of the module has to do is use it to listen, and they'll get a channel of packets that are accepted by the filter coming right back to them. And then it uses the context package because I thought it would be cool, but it doesn't really help that much. Yeah, so this is what I talked about earlier with the TCP fast open. Basically, you can send data in the initial SYN packet, but in Go, at least the easiest way to do that is to build the packet yourself. This took a minute just because you have to look at Wireshark and you have to make sure that like the version matches up, IHL matches up, you put a TTL that makes sense. You have to make sure that the headers and checksums are being calculated, and then you have to use the Go packet module in order to actually serialize it. But it's very well documented, and it's been done a bunch of times, so I didn't do anything too revolutionary there. And since we can build our packets, now we can expose send, where all we need is a file descriptor, so that's our socket for sending, a destination IP, the layer 4 protocol you want to send it as, because at this point TCP and UDP don't matter, and the layer 7 protocol, which also doesn't matter, but it'll help control the port, and then that can just send the packet. And so why kind of do all of this? Working with low-level BPF made it really hard to do some very basic things, but it also made it very interesting what was able to be accomplished. And there's like a cool answer up there, but the honest answer is it made a really cool red team tool. Basically, I could have a host have all of its firewalls drop every packet, and as long as you could reach that virtual machine, in other words, as long as there wasn't a network firewall blocking it, you're able to run commands on it, you're able to send it on TCP, UDP, over SSH port, the DNS port, and it doesn't matter. And you can run all those commands, and you can hide it in a service and get it running very well. You can see like I made a horse file for proof that it can actually create stuff, and that's the public IP for routing across the internet. And it's kind of a gimmick. It's kind of fun. You could hide it very well, but mine's not hidden particularly well. I was more interested in making this functionality actually work. And also, Girard will be like, whoa, whoops, that has a swear in it. Sorry, guys, I forgot that screenshot was there. Girard will be like, wow, that's really cool. I can't believe that Linux can do that. And he's just being nice to you, but it's still cool to hear him say it because he obviously knew that BPF was in the Linux kernel. But yeah, so if you're able to get this far, and this wasn't just total nonsense to you, which I know it kind of comes off that way, it's really easy to build a layer 7 protocol on top of this. And so that's kind of my next step. And so you can put in your own version of TCP that has like silly functionality, your own version of whatever protocol you want, and you can build like some really cool stuff with BPF. And if you learn eBPF, you can get into like messing with how Docker returns, because Docker uses local networks. You can get into like really fast big data processing and just do some ridiculously awesome stuff. That's a shameless plug for RII. And yeah, I have a blog post I'm working on for it. It's kind of cut off, but you can see the repo down bottom there. And in the blog post, it'll go much more in detail about like how I picked which packet I did and how it actually communicates, how BPF works at a much lower level, and those sorts of things. But yeah, I know there's a lot of nonsense, but this was a lot of like the hard found information that I had trouble finding, and now I have it in one place, hopefully, so that I and other people can come back to it. Because it is really confusing. It's hard to work at the lowest layer of networking, but it is really rewarding when finally you see packets going across the internet and you're like, oh my gosh, I'm like hacking the world right now. But yeah, thank you. Hello, James Southcott. Yeah, so the funny thing is that, whoops, we're just gonna. Yeah, so the same module that has the listen actually has a send function in it, so that's exposed as a Go module. But really, the interesting thing is that if you're listening, it actually doesn't really matter how you send the packet. As long as the data section of the TCP or UDP packet that first hits the host has your magic bytes, then it'll interpret that packet however you want to. Because at the end of the day, all this looks for is that. I haven't written the Python module to do that, but if you use Scapy, it takes like 3 seconds. Or if you're in Java, it's a little bit more contrived, but it's not extremely challenging either. That's facts. Yeah. 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 That's big facts from the chief over there, Red Team Chief James Healthcott. Yeah, I'll probably do that. This is on pause for like 2 minutes because I'm falling into the semester, but now I know what my immediate next step is going to be. Joey, you look like you have a question. That's okay. Shouldn't you be working right now? Yeah. Anyways, that's the end of my presentation. Oh, hi, Luca. Luca asked me, what would I use if I wanted to break into someone's home? Probably the gift I forgot I was about to gift. Wow.